All right, so we are, this is how it's working out. And I promise you guys that I will get you a schedule for presentations um, within the next, before next class, before the lab. But we have actually 4 classes, and then we move into, 4 classes with expository or lab material. And then we move into you guys doing presentations back to us. Actually, we move into a test, and then after the test, we move into to you guys giving presentations back to us on your projects. So we have this week where I'm talking about databases, and in particular, we will do some stuff on Mongo databases, MongoDB. We'll see how that goes. And then next week, I'm completely relearning everything I know about TensorFlow because apparently, as of October 2019, TensorFlow went to a 2.0 interface. And none of the stuff that I had in there about building graphs and executing the graphs actually works anymore. Yay! I expect that there's a way around it, but they also have a much more streamlined interface that looks much more like just using Python rather than actually going through and building a graph and executing it. So that's kind of a good thing, I guess. It's simpler to use. It does, however, mean that everything that I knew about TensorFlow, which I don't use all that often, is now completely obsolete. So we will pick up and we will do that. So this week is databases. Specifically, we'll talk a little bit about Mongo, and then next week we'll talk about TensorFlow. Any questions? After that, there's no more. We have a test, and that's pretty much it. In fact, if we look at our schedule, I guess I can pop in here and look at the schedule. Come in, we'll do some presenting slides. If we come down here and look at the resources, and of course I'm not on the slides page, I am on the image of the slides page. There we go, here's the slides page. If we look at the resources, we look at the schedule, we are sitting right here towards the end of the semester. Way down here. Okay, so yeah, so we have a test on 2 weeks from today, and then we will start our project reports on that following Friday. And hopefully we'll be able to get through all of them in 3 days. I think we will. I think we'll be able to do that and still give you all some reasonable time to talk. All right. The other thing I'm over here for is I wanted to go down and show you where today's lectures are, just in case you're still not able to find the lectures. I figured it was time for a review. Come down, modules, databases, this is where we are. If you download all of this, what you'll find is we have a make file here and a source directory. So if you go into the source directory, Google is actually pretty good about showing you stuff. Oops. If you don't wildly click on stuff that you don't actually need to show. So you can actually look at the index. It's a restructured text file, and you can get most of the slides there. Right, so if you just want to review it online. But if you want to actually run these, all you have to do is have a LaTeX installation with Sphinx in it. You go down into the databases directory. You can see we have everything here, including the source file and the make file. And you just do make slides, gives you the slides. You can also do something like make, once this runs, PDF LaTeX. And that will tell you can't do that. But if you instead change this to LaTeX PDF, it will build you a document. And you can also make HTML pages if you want. So this is all, multiple ways of actually generating the material into a viewable format. I use the slides when I'm actually presenting to you guys. Okay, so let's get started on today. Today we want to talk, Today we want to talk about databases. I'm going to throw myself up in the bottom corner so you guys feel like you're being addressed by an actual person as opposed to a disembodied head. That's supposed to be better for getting people to pay attention and comprehension. I'm not sure I believe it, but I've got all this camera equipment. I may as well actually use it. Okay, so, and I'm again not on the page. I am on the image of the page. Okay, so again, this whole module is licensed under CC by SA 4.0. It's pretty much what we've been using going along. And this is important because we actually did take some stuff from Raymond Jacobson back in, he's from the class of 2016. Back in 2015, he actually did an internship at MongoDB and came out of there a full evangelist and wrote up some slides that we managed to use. You can see his original slide here as a Mongo, as a PDF. He has some stuff in there talking just about the company culture and about what he, his experiences were as an intern there. So it's really nicely done. And we took some of that and then extended it. And then, of course, as we had to, as technology marches on, you can pull this down and see it. I don't think it looks like the PDF isn't rendering. As time marched on, we have less and less of his stuff there, but still, he was the impetus for starting this module way back in 2015 before I was ever involved with this. And then, of course, there is the actual Mongo documentation out here at tutorials point. So, make sure you have this stuff available to you when we get to our test. You may have learned from the last test, we don't do we do open book tests. You're allowed to use any of the material that we allowed you to have for the labs or that we called out in lecture. So make sure you have it. It makes it a lot easier to take our test if you actually have this material available. Question, am I recording? And yes, I am recording, so that's good. All right, so that's kind of and then, of course, there's the Mongo manual. Read up through the CRUD operations. I think if you do that, you're doing pretty well. You should be able to see that. We could do, people teach entire courses on databases. We teach a couple of them here, or multiple courses on databases. So it's hard to make you read all of this and understand it for a test, but come down through the CRUD operations, right? If you remember, CRUD are the major, particularly distributed database operations: create, read, update, and delete on documents. So, read down through here, know about this stuff, be able to kind of use it, and be able to well, it'll help you with the lab, it'll help you with life, etc. Okay. And that should be introduction. We'll probably have another modification. I'm fairly certain that was a typo I put in rather than Morthy or our student. Because I have to keep you would think after giving this multiple times we would have all of the typos out, but fortunately we make new typos every year. So let's just start from the beginning. If you've had a database course, you're probably, I think that this is going to be pretty easy for you, but you probably did SQL. So we're going to talk a little bit about non-SQL ways of doing things, because SQL isn't the only options, and I don't know how much we get into those in our database systems, but it's good to be exposed to those, and it's good to get, even if you haven't taken databases or don't plan on taking databases. I didn't have a database course until 2/3 of the way through my master's program, where we actually had to write the database, which was much more fun than using databases, I thought. Anyway, a database is an organized collection of data, generally stored and accessed electronically from a computer system. Notice that generally, where databases are more complex, they're often developed using formal design and modeling techniques. So what does this mean? This means that before we got these formal modeling and formal design and modeling techniques, we developed databases, but they weren't always so well organized. And in fact, what you would find is that a lot of people had hierarchies of files on their file system, and those hierarchy of files were in some sense a database, where if you knew the organization and you knew what you were looking for, you could go from one file to the next and actually find the information you wanted. We called those flat files as opposed to database. Didn't have a good interface. All the access to it was either editing or reading files. But that's after the advent of the whole idea of storing data on disk. Before that even, we had these weird looking things that I haven't been into in, well, at least in the last year. I guess I used to go to the RPI library to get coffee every now and then. But this is called a library, and it is essentially a database, right? We have collections of reference materials that you can go for, and they look different now. That's a more modern one. Here's one you might be familiar with, including the position of the park benches there, or the picnic tables. So, and here's, basically sitting around a tray. This is the new replacement for it, right? You have a bunch of terminals connected up to a mainframe, or maybe that's a network connection to an online database. And now these are kind of the replacement for the other types of databases that we used to have. Now, the thing I want to call your attention to is, if we consider this a database, right, then it houses different collections of data, right? We can go to the fiction section, and we can get books or documents on the fiction section. We can go to different journals, and there might be a whole sequence of journals from ACM or from SIAM or IEEE, right? And those collections, within those collections, there will be separate documents, and those documents will be the actual text of the different volumes that the library holds in its collections. And that's kind of where we want to get to as we kind of progress through this, is this conceptual organization of, you have a database, and a database can have multiple things in it, and within those multiple things, what our goal is to store information, kind of as either distributed or coherent documents that we can actually access. We'll go back in the Wayback Machine. This is I was not doing computers until at least 77, and then it was pretty mild. But if we go back early enough, what we're actually starting out with, and why, nope. How do I make that go away? This top bar. Okay, we'll just have to live with it. I don't have too many slides that go up that far. So that helps a little bit. All right, so if we start off, we're going to look at something called a relational database. So the idea between a relational database is that you have multiple tables of data, and you store information in those tables of data, and when you have additional information, you have another table. So for example, if we have a table of professors, and we know what their favorite piece of software is, and I don't think Professor Goldschmidt's favorite piece of software is Notepad, but maybe. Professor Cutler certainly likes Dr. Memory, although I think maybe now it's Smitty. You know, if we know this, we can make an association between a name as a key, the professor, and some information about what they want organized, you know, using a schema as, you know, their name, their favorite software, Morphe Observatory. Observatory is a software that runs Arcos, soon to become Telescope, hopefully. Magda Nishmael, LaTeX, Cutler, Dr. Memory. And then maybe later we have more information about the software that they like that we want to include as well. And we don't want to put it all up in here because, well, we'll talk about why in just a second. But, you know, we may have the software Notepad. We want to know what platforms it runs on. We may want to know its release date, etc. So we have additional tables that kind of talk about different components where there's more information available. And then we can do things like this. We can use SQL to do something like select favorite software from professors where name equals Morphe. And what that'll do is it'll go into our table, right, from professors, right? So we'll go to the professors table and we will select, we'll print out the favorite software field where the professor's name is Morphe, and that would give us observatories. That's a simple query on one database. And then what we want to do when we get more complicated, if we want to find out, for example, knowing that Morphe's favorite software is observatory, and this slide is wrong too. Oh no, I'm sorry. This is not the synthesis. This is the comparison. You know, so knowing that Dr. Morphe's favorite software is observatory, maybe we want to find out what platforms it runs on, or maybe we want to find out who, as our query down here says, who likes software that's cross-platform, right? So that means that we need information from both the software table and the professor's table, right? Because we want to know the names, and the names are only stored in the professor's table. So now we're going to do something called a join. And what that's going to do is we're going to say, all right, so I've got information in multiple tables. So I want to take these two tables and I want to put them together. And the way I want to put them together is I want to take the favorite software field and I want to pull in the data from the software table. That's the name of the software stored there. And I want to use those to make a record that I can then query looking for cross-platform software. And what I'm interested in is I'm interested in the people's names that goes along with this. So if we look, Professor Cutler likes Dr. Memory. Dr. Memory is cross-platform, so we would like Professor Cutler to be there. Professor Magda Nishmael likes LaTeX. LaTeX is cross-platform. We want Professor Magda Nishmael to be there as well. Right, so this is just saying, let's take these two tables, let's figure out the field that they have in common, and we'll use that field they have in common to do a synthesis of the data. And having done that synthesis, now we can ask different questions, right? Because we couldn't answer the question about who likes cross-platform software from the information stored in any one table. And this works pretty good. When we do the synthesis, when we do the join, it kind of looks like this, right? Goldschmidt likes Notepad. Notepad runs on Windows. The release date was 1983, right? So Goldschmidt likes Notepad. Notepad runs on Windows. Date 1983. Morphe likes Observatory. Observatory runs on the web, right? Observatory runs on the web. 2010, and etc. So this is kind of the synthesis table we get from the join. And, you know, having this synthesis together means that we can answer questions about the combined data in both tables. Right, and this is the idea of relational databases. Right, you have tables that have relations, and the relationships are defined by common keys, or common, you know, yeah, defined by common keys or ways of putting the tables together, and then you can kind of parse down those relationships to answer more complicated queries. And that sounds complicated, and in some sense it is, but there's some really good ideas behind it, right? So first off, you can update the software without having to touch anything else, right? Which is really good. You have everything separate. It's normalized, One table doesn't interfere with the other table, and you don't need to keep around redundant data. Now, almost no database in practical use has all redundant data eliminated, but there's really good reasons for not wanting redundant data. And one of the reasons is, what do you do when all of a sudden your redundant data no longer matches? And this comes about all the time, right? You have redundant data, you update, you can see this in your own code development, right? You have redundant data, redundant code, you've implemented an algorithm multiple places instead of encapsulating it in a function, and now you are changing one of those, and now depending on which function you call, or depending on which code you're executing, the results of your specific algorithm are giving you different, are different. So redundant data is bad, very bad from that standpoint. If you update it for one person, you have to update it for everybody. Or if you update it in one place and you have redundant data, like let's say that in our original table now, let's say that Notepad has now been migrated and it's cross-platform, and now if we have redundant data, if we have the Windows field, if we've actually storing this table instead of our two combined tables, right, that look like this, everybody who uses Windows, every record that uses Windows would have to be updated to be cross-platform. Whereas if we have the separate tables with no redundant data, we can do it right here. So not having redundant data is a great thing. Makes sense. And it allows us to kind of divide things up. We can store our tables on different machines. We can do all sorts of great things. And quite honestly, this is my wife. She's been working in databases since, well, at least 1993. And she's still using SQL. So it's not like this is an old technology that's kind of obsolete. They are still using this. They try to keep things normalized. She will tell you that they fail. She will tell you that their tables contain redundant data. But they, to the best part, to the best of their ability, they try to keep that separate, and it still seems pretty sensible to do that. So in the 70s, 80s, and 90s, this was the paradigm, and probably even today. But let's go back to the 70s, 80s, and 90s. The Oracle database was, the initial version was 78. IBM came out with DB2 in 83, MySQL 95, Microsoft SQL Server 89, right? All of these SQL or relational databases were released in the 70s and 80s and even into the 90s. This is the world they lived in, right? So you had massive hard disks that held very little bit of data. And this is already old, right? I think we can get 2 terabytes now, or maybe at least multiple gigabytes. I'm not sure we hit a terabyte at this size yet. But this is 2-3 years ago. 128 gigabyte drive using USB 3.0 was about the size of a dime. 250 megabytes, 128 gigabytes. We might have a blog, or at least some web data that one person wrote and maybe a handful of people read. And now we're in a situation where we have something like Facebook, where if you go to LinkedIn, for example, I have 1,000 or 2,000 connections. It's like, why would 2,000 people want to be connected? And it gets bigger, right? And it also gets segregated into tribes, right? We have people following different groups, but the reality is that there's just this massive networking, massive reading and writing. Databases are widely distributed, right? If you're saving if you're using Facebook, if Facebook is using a database to maintain all of its blogs and all of the stuff you write about the cute little kittens, it has to be something that's accessible, not to these 3 people who may even be willing to wait a couple minutes while you pull something up, but to these massive masses of people who are actually trying to get to the data. So the kind of point we're trying to make here is that we're kind of living in a different world with different requirements. The SQL world, to a large extent, was a much when SQL was invented. And again, I don't like being too hard on it, because it is still probably the most one SQL derivative is probably still the most widely used around. So it's working very well in this world as well. But this was kind of the environment it was kind of designed for. You had small access, you had limited amounts of data, and so by breaking up the data, you could do these joins and kind of synthesize bigger data based on these little these little snippets, these little tables all around. 2015, from 2013 to 2015, 90% of all the data in the world has been generated over the previous 2 years, right? So I don't have a graph for 2021. I expect that it has continued. If you look, that's kind of an exponential. I expect the trend has continued. I certainly think that looking at the recent advances in AI and TensorFlow and machine learning, you have to posit that our data generation or data aggregation has gone up at a continuingly high rate. So we're generating now massive amounts of data, and we have people, massive numbers of people actually trying to access that data. So let's look at what our joins and what our normalization does for us. Well, if we are on the same computer, right? So if we're doing vertical scalability, as we get more data, we scale up to a bigger and bigger and bigger system. Things don't work badly, right? All of our data is available. We do have this combinatorial problem that if there are 100, professors using Notepad, right, we have to go into this table 100 times to find Notepad. So we do have a little bit of a combinatorial problem using our joins. But in general, if all of the data is together, this is not a horrible operation, right? It's vertically, it scales reasonably well. Again, we have this problem as you get sufficient numbers of people in there, right? You're doing this one-to-many mapping or many-to-one mapping, and you have to go through and you have to keep reading through all of the software over and over again in order to join up your records correctly. But there are efficient ways to do that, and it's not, if we're using hash tables, perhaps we're hashing the keys, we're probably pretty fast on that, so long as all the data is immediately available to us, so long as we have it living on the same machine. But that's not where we live anymore, right? So now we have this new paradigm where we have massive computers, or not instead of trying to build one massive computer that does everything, we have things like parallel computing or distributed computing, where we have parts of our problem stored on multiple machines that are interconnected by the internet and may not even be in the same part of the world. And now if we start looking at this whole join thing, the join's starting to become more expensive, because in order to do the join, if we're storing our professor's table on one machine and the data that we need to complete the join is on another machine, now all of a sudden we have to fetch all of this information across the internet. The internet's getting faster, but it's not getting faster that fast, right? So this is now a very expensive operation. It's still, right, if we're fully normalized, it's still very safe because we can't have any redundant data. We always come back here. That's part of the reason why we don't want to do too much caching, because we always want to come back to the appropriate. We don't want to have this stored here and here, right? We want to have it stored one place. So somebody's going to have to pull it when they need it. This whole distributed thing makes the database start slowing down. And you'll see this even if you're in a cluster, as opposed to truly doing this over a distributed, different computers on different parts of the world. And of course, you start getting these really big schemas that show where everything's stored and what fields are in each part of the table, etc. again, I'm not against normalization, by the way. If you can get away without having redundancy, it's really good. And you can see that how this maps into the software that we actually generate now as well. So for example, if we have a class audio device that is the exemplar of all audio devices, things that take in some type of music format and give out sound, well, we can say that pretty much any device is going to have a device type. Self.device would be our device type, and a manufacturer, somebody that actually created it. Some things maybe have more than one manufacturer, and then we can kind of subclass from here. And maybe our MP3 player has a file format that it'll read, and maybe our record player doesn't have a format it'll read. It'll only, it reads records. It's not really a binary file format, but it does have a speed, because record players could play records of different speeds, and maybe we have a record player that only has one specific speed. And right, overall, our data is like this, right? We have a device, we have a manufacturer. If we are not a record player, we have a file format, and if we are a record player, we have a speed. And this is kind of like the mega table, right? All of our fields are represented. It's not well normalized because we have these places where the schema just doesn't handle the fact that an iPod doesn't have a speed. But we can normalize it, right? And we can have our devices, our file formats, and then we can pull out the common stuff, right? So after we pull out all the common stuff, we have all of the stuff that's common to everybody here, and then item-specific stuff for the turntable, the speed, for the iPod and the Zoom, the file format. They can be in separate tables. And the whole idea here is now we've done a decomposition, and this is what normalization is, right? It's taking your data and decomposing it into segments that make sense, get rid of redundancy, and make separate tables holding that data, so that you don't have missing data. All the fields are there in every table, and you can use joins to get additional information out. So for example, if we want to find device turntables, we want to find out their speeds, we would do a join between this table here and this table, and we could find out for the project manufacturer, we could find out that they manufacture turntables with 33 RPMs, etc. All right, kind of makes some sense. Okay, so that's kind of a bird's eye, 10,000, 20,000 foot view of relational databases, SQL type accesses. So now we want to ask ourselves, how does MongoDB differ? Or how does a non-SQL database differ? And MongoDB is the exemplar of this. It's not the only database that does this. I'll show you a couple others a little bit later in our presentation, based on some of our students' data. But we have CouchDB, we have Cassandra, I believe. If you want to go way old school, we have something called MUMPS or M. I think I mentioned this a few previous lectures that did this for electronic health records in the VA. So all of this is still available. The idea here is that our schemas are vastly simplified, because instead of breaking things up into multiple tables, well, we just ignore this whole redundant thing. We take the concept that our memories now, our data storage is huge. So we can afford to have a little bit of redundancy, at least as far as memory goes. And our joins are expensive. So instead of doing a join, we want to keep all of our data right within the same record. So if you look at this, right, this is Mongo is a document database, right? We talked a little bit about this, about our libraries having collections, and within the collections we have documents. and all of our data is stored in our documents. And this looks a lot like JSON. If you've done Python, it looks a lot like how a dictionary in Python is represented. It's actually BSON, which is a binary version of Python, of JSON. Binary encoded serialization of JSON-like documents. But when we're looking at it, it pretty much looks exactly like JSON. It's just that everything has a specific type. Come on, go back. And you can check that out on your own. But the idea here is that for instead of having a schema that lays out what each of our fields are, each one of our fields is encoded with a field identifier and then some data. So for the field, and by the way, we're going to maintain a unique ID for all of our documents. So this ID field is pretty much standard. You need to have something like that. But this ID is 1, 2, 3, 4. Then we have author. Well, the author is itself a document with a name and an email, right? And then we have a post. This would be like a blog post. We can have the date of the post, right? And this is of a date type. This is GPS coordinates. We can have a list of ratings, right? We have 2.2, an overall rating of 2.2, and along with that overall rating of 2.2, we have an array of comments, and then we can have tags. So the whole idea here is that this is really pretty unstructured, right? We have a blog tags, and we have a blog post, right? The blog post has tags, it has authors, it has comments. Those are these, right? These fields, they're sub fields in there. I would probably throw in location as well, but it's not in there right now. Anyway, so we have this type of information, and we don't worry about redundancy, and we don't worry about not having all the data. What this allows us to do is that instead of having our data stored all over the place in different tables that may not be on the same machine and have to be pulled together in order to answer specific questions about the post, is we store it all together in one little block. And if we're going to distribute it, what we'll do is we'll distribute other records, other documents on a different machine. So we have immediate access to all the information to answer any question as long as that record is stored on our machine. We don't have to do any joins that cross boundaries. Maybe to look through our entire list, we will have to do a join. But then again, since we have this large memory, right, what we can do is we can just store records redundantly on multiple systems, particularly if I'm looking at the blogs database. Well, maybe somebody else is looking at the blogs database too, and we just replicate the data, and we don't worry about that small increment for replicating parts of our data. Now you can see the problem here, right? If I'm not just reading this data, I'm instead modifying it. At some point, we have to come up with a way for making sure that this data is reflected. And there's different strategies for doing that. MUMPs use the eventual, I think it was called eventually everything will be, come on, go back to where you're supposed to be. There. Eventual synchronization. So changes would be replicated through the network until everything was up to date. But you were never assured that when you made a query that the data you had was necessarily up to date at that specific time, unless you went through and did a resynchronization before every query. And now it's, I'm on the image instead of There we go. So the beauty of this is, if you do this, it does give you yeah, if you do this, it does give you better performance, right? Because you're not doing an expensive join, particularly a join that has to go across distributed nodes. You can be looking at your data while you're fetching the next bulk of data. But again, there are some drawbacks with that, with regard to redundancy and making sure that you always have the most updated data. So these are just some data points from the presentation showing that Mongo is much faster than Postgres for data load, select, insert, and as the database size goes up, and the trade-off is, however, this database size goes up because you're storing redundant data. So select and insert go faster, but you're paying that price with more memory, but memory is cheap, so nobody cares, right? And these are different workloads that, again, show when compared to some of its competitors, Cassandra, Couchbase, and MongoDB, in terms such as insert, read, read and update, etc. That, again, MongoDB is a very performant system. And it is, or was. And here's the other part. It has a flexible schema, so you don't have to worry about all the fields in a relational database. Data that isn't there is just not there. So if you don't have the tag, right? If you think back to a Python dictionary, if you don't have the tag, you don't have the tag. You just have to make sure the tag's there before you try to query the data. So it just won't show up. So in Mongo, it just becomes a matter of you start up your database, you insert some data. If you want to change the data, you change the data, you insert data with new structure. If you want to go back and change everything, you'll have to read every record and update every record. But you don't actually have to do that in general, right? You would just start entering new data with the new fields, and you would assume that data that of the old type would not have the fields that you added to the schema, which is different than a relational database where you have to actually set up the schema. You have to insert the data. If you want to change the schema, you have to specifically change the schema, insert data with the new structure, and you also have to go back and retrofit your database. Otherwise, all of the data that you had before is garbage, right? And you have to make sure that the schema isn't breaking, etc. So it's really a much simpler way of doing it. I'm not gonna claim it's better. I'm gonna claim in some instances it's a better way to go about doing it, and it's a different view on actually doing databases. So here we go. This is just an illustration, right? Maybe we're searching for specific tags. Bob Davis didn't put any tags on his blog post. So if we're searching for a tag and we're trying to find Bob, we're never going to find it because there are no tags, right? So this data is not consistent, and not all of our blogs are stored the same. All right, so this brings us to an interesting part of the conversation, and I don't know exactly how this is going to work. So we're going to kind of talk about this a little bit. So Mongo started out as an open source software, and in fact it was licensed under the AGPL. Do I have that in here someplace? And it is still out there on GitHub. Right, so you can come to GitHub and you can get all of MongoDB's code. Eventually, if you're patient. There we go. There we go. MongoDB database. Come down in here. Right, this is all available, and it was open source, or so it was licensed up until October 10th of 1998, I think. It was licensed under the AGPL, which is the Affero GNU public license. We can go in and let's see. I think this is in the README even. Right, free and the source is available prior to October 16th, not October 10th. Released under the AGPL. All versions after then, including patch fixes for prior versions, are published under the server-side public license, and you can see the individual files for details. And they did this because, well, when they were starting up, they found open source to be really useful for coming up to speed quickly and quickly getting market penetration. And, it made it easy to adopt. You just had to download the system. There was a lot of trust in open source. They were able to build up a community, and they did build up a community. I used to go to conferences, and they were there all the time, building community, reaching out, talking to people. They used open source for all of the right reasons, and it allowed them to grow really quickly. But now they have this other license. And the difference between the AGPL and the server-side public license in kind of TLDR terms is that the AGPL, it comes down to the terms of what distribution is. Or actually, let me take this back a little bit. So what had started happening was MongoDB had become a very popular database, and places like Amazon in their AWS boxes did not actually need MongoDB support. They offered their own support for people running on AWS who might be using MongoDB. And what MongoDB found was that a lot of AWS and other distributed cloud providers' systems were running MongoDB and weren't providing what they thought was sufficient support back to MongoDB. In other words, they couldn't find a way to make money off of somebody else running their code. And that making money off of somebody else running your code is a big part of being able to it's a big part of the open source definition, right? You're providing code out there. You're not putting any you can't prohibit somebody else from making money. They used the AGPL at that point. So the AGPL required that if you were linking to it or providing distribution to their code, any changes you made to their code had to be released open source, right? So even the AGPL said even the act of allowing somebody to connect to a server and use the code was in fact a distribution. That was the big clarification of the AGPL versus the GPL and the LGPL, right? Connecting to an instance, connecting to an AWS node, and using MongoDB there was a distribution. So you would have to open source any changes you made to MongoDB and release those. The problem was MongoDB was a standalone system. It was fine. They didn't need to make any changes, and if they did, they were happy to. Amazon was happy to release those changes back. They weren't competing with MongoDB in the database department. What they were doing was they were just providing a setup that had MongoDB on it, all of the software you needed to generate a system, and allowing people to connect and use it, and people were paying them for the privilege of being able to do that, right? Mongo didn't like that because they weren't getting, for all of the installations of MongoDB that were on the AWS, and I'm using AWS as an example because it was one of the big ones, but it wasn't the only one. MongoDB couldn't get any revenue from that. Those people weren't coming to MongoDB to get database support. They were going to AWS to get AWS support. So what they did was they came up with something called the server-side public license. And the gist of the server-side public license said that if you are distributing something in terms of the AGPL, distributing our code in terms of the AGPL, and you're making a certain amount of money, or there were some critiques about commercialism. I don't remember the exact terms there. But if that were the case, then you had to open source the entire ecosystem used to support that node, which meant that Amazon was faced with having to open source all of their code that was running on these nodes, or not using MongoDB, or purchasing. The whole idea for MongoDB was to get some money. So their hope was that my understanding of their hope was that places like Amazon would fork over some money for a license that would allow them to keep their own code proprietary. And that didn't happen. So it was kind of a nasty little thing. Instead, AWS, I think they started from a previous Mongo branch and developed their own database. Stopped using MongoDB, I believe. You can check that out. MongoDB, tried to I believe start up their own servers. It's just I think it was kind of a lose-lose situation for everybody. We lost access to MongoDB in the open source world, and MongoDB actually lost market share because they're no longer being used on things like the AWS cloud servers, at least to the same extent that they used to be, at least as part of a standard distribution. I'm not sure. I haven't looked into it. You may still be able to download it yourself and run it, right? Because that would not be them providing an AWS node with MongoDB. That would be you standing up an AWS node and installing your own software, which wouldn't be them distributing it. It would be you installing it. Anyway, there are a couple of. That's essentially my understanding of what's actually going on, and that was a couple of years ago now. It would be interesting to go out and get some statistics. Unfortunately, I wasn't able to get anything in the amount of time we had. But I would be interested if anybody has any additional insights into that situation. Wrong window. Any questions before we kind of go on from here? I think we'll talk about this. At least there's the possibility of talking about this in the lab, but let's kind of see where we get on this. So there are a lot of issues with databases. Databases are still a very popular topic. You have issues with scalability. How do you grow? How do you grow distributed? How do you solve the redundancy problem with a database like MongoDB, right? How do you ensure that if you have two people making inserts and deletes and changes on two different parts of the same table, how do you ensure that all of the correct answers are getting resolved in a distributed environment? What do you do when a node goes down? Fault tolerance kinds of things, availability and consistency, and certainly speed. And speed is the one that these non-relational databases actually have an advantage on, because they don't actually have to do these joins, particularly joins across the network that can be very time consuming. There are a lot of options. If it was a solved problem, you would expect there to be much fewer options. These are some: Cassandra, Redis, Mongo, CouchDB, Hadoop. These are the ones that were available 2 years ago. I think there were more 2 years ago. These are what I chose to put up in little slides because I had cool little items for them 2 years ago. And we can actually go in and look at, by the way, I tried to update this one. There have been no updates to this since 2019. I guess that's not so surprising. But basically, Oracle is the first available database. It's still one of the most popular. MySQL, I believe, is open source. Oracle, I don't believe, is open source. MySQL, SQL Server, that one I don't remember. PostgreSQL, I believe that's open source. MongoDB, it's not quite open source anymore. And by the way, they did actually apply to the OSI to have MongoDB declared their server side public license declared as an open source license. And that dragged on for a long time. And at some point, you may have started hearing a lot of FUD about who owns the definition of open source, and we can call anything we want open source. It's just like calling something all natural or organic. The terms have meaning, whether they're formally allowed or not. So that was the big thing that was playing out on two different fronts. They were applying for, or they were trying to convince OSI that it would be a good idea to declare their license an open source license or in compliance with the open source definition. And the OSI was balking, and at the same time they were attacking the whole definition of open source and saying open source is what we believe open source is. Anyway, here's IBM DB2, Redis. I think Redis has similar problems to Mongo. SimpleDB is from Amazon. So you can probably see that it's another NoSQL data store. So this is kind of their response, I think, to MongoDB, although it may have predated MongoDB as well. Microsoft Access, I'm not sure I would consider that one a viable database, but it is in the top 10. SQLite. All right, so these are all, these are just 10 fairly popular databases. A good number of them, at least 3 or 4, are completely open source, and we've got a couple more that are kind of open source. All right,